Today is the 9th of October, 2017. So anything directly near the surface of the Earth falling with constant acceleration. When we say near the surface of the Earth, we basically mean within the atmosphere. The atmosphere, hey, what demonstrates the limits of Earth's gravitational pull? They all look around. They all look at one another. They all look sideways out of the corner of their eye. The upper end of the atmosphere. Why? Because what's holding the atmosphere in place? Gravity. An object has to be large enough to hold even very light particles, like gas particles, to it. That's why the moon has no atmosphere, but we do, because the Earth is more massive than the moon. So the more massive a planet is, or an object in space, we should say, the more ability it has to hold things to it via gravitational attraction. So anyway, yeah, within the atmosphere. If it is falling within the atmosphere, it falls with a constant acceleration known as g, and it is 9.81 meters per second squared. Now, that's not the real number, obvious. I think it goes to, what, 9.812 something. I forget all the digits. But we typically use 9.81 meters per second squared as our approximation. So gravity is towards the center of the Earth. We show down as a negative. So we most often give acceleration of objects in free fall. A equals a negative g, which is negative 9.81 meters per second squared. Meters per second squared. I need to fire my slide editor. Okay, that's easy enough. You may have even come up with a number that's similar. If we were doing order of magnitude estimations, we'd say, 10 meters per second squared. 10 to the 1. But here we're doing real numbers. Come on. Okay. Here's the part that's hardest to grasp, typically, and to remember. When the only force that's causing acceleration is gravity, that gravity is 9.81 meters per second squared down, period. So if I jump up in the air, the minute my feet leave the ground, what is accelerating me? Gravity. Nothing else. Unless I got a rocket pack strapped to my butt, nothing else is accelerating me. Once my feet are no longer in contact with the ground, the only thing acting on me is gravity. When I throw an object, I have no objects that are good to throw. Here we go. This is relatively harmless. That's what somebody always says before somebody gets hurt. Nothing bad could happen here. Sorry, I was kind of thinking you might catch that, Corey.
I was very unaware.
Oh, I'm sorry. Here, Jeremy, do you want to try? Okay, I'm bad at throwing. Are you bad at catching? Excellent. Marriage made in heaven. Okay, good job. The minute that thing leaves my hand, there's nothing else, and it's not candy. You probably don't want it. It's a really disgusting herbal cough drop. Oh, thank you. I appreciate that. The minute that thing leaves my hand, there's nothing else acting on it. The force that my hand was exerting on it is done at the moment that those two things are no longer in contact. So at that point, the only thing that is accelerating that object, and remember, acceleration can be positive, negative, it can mean speeding up, it can mean slowing down. The only thing accelerating that object is gravity. So its acceleration is 9.81 meters per second squared down, period. If I toss that same cough drop straight up into the air, its acceleration going up is the same as its acceleration at the top, is the same as its acceleration on the down trip. 9.81 meters per second squared, down, always. In free fall, there is only one acceleration. It is 9.81 meters per second squared, down. This person, well, okay, and we say ignoring air resistance. Obviously, they're spread out because they don't want to ignore air resistance. But in the absence of air resistance, they are accelerating at 9.81 meters per second squared, down. This ball, which is supposed to look like it's being thrown upward at the moment, it's accelerating at 9.81 meters per second squared, down. Even if it's traveling up, it's accelerating down. These baby turkeys, if they jump to the top of their water container and jump back off, will accelerate at 9.81 meters per second squared, down. I think I overstated that whole 9.81 meters per second squared down, but it's important, so it bears repeating. Here's the part to be careful with. Sine. So, because we have done this whole thing of artificially imposing a Cartesian coordinate system on the world, we use sine as a proxy for direction. So in our little self-imposed Cartesian coordinate system, you know, this quadrant, here, I'm going to stand with my back to you. This quadrant is positive, this quadrant is negative. Don't get me started on left and right. In that same self-imposed or artificially imposed Cartesian coordinate system, up is positive, down is negative. We then take that and play with the compass rose and go, north is positive, south is negative. Well, if you're looking at it from a north-top orientation, that's true. But when we're talking about things falling through the air, by convention, we call the direction of travel towards the Earth, if we're talking about the y-axis, to be negative. That's pretty simple. Okay. G. Be careful with this one. Magnitude is 9.81 meters per second squared. That's the magnitude of acceleration due to gravity. You generally see it as negative 9.81 meters per second squared. You're generally using negative g. Why? Because acceleration due to gravity is towards the center of the Earth. Remember, you are very, very attractive to the Earth, and specifically to its center. Eat a lot of Christmas cookies, eat a lot of Halloween candy, you will become even more attractive to the Earth. So, the more sugary treats you consume, the more attractive you are to the Earth. We're going to walk through a sample problem, and then I'm going to set you loose on the 2F problems with a couple of cautions. So we have a falling object problem here. Jason hits the volleyball so it moves with an initial velocity of 6.0 meters per second straight up. Would that be setting it? We don't know. If the volleyball starts from 2 meters above the floor, how long will it be in the air before it strikes the floor, assuming that Jason's the last player to touch the ball before it hits the floor? So let me shrink this down. And it is quite helpful in these cases to draw the picture. So there's 0. There's the ball's travel upward. We know it's going to then travel downward. We have a VI. We have a delta t total. We have an acceleration. Do we have a displacement? Yes, we do. Because that ball starts 2 meters above the ground, delta y is this distance. What is that distance? Be careful. You can get the magnitude of it easily, right? What's the magnitude of the displacement? Two meters? But what's the direction of the displacement? It's downward. So delta y is negative 2.0 meters. Okay. VI is positive 6.0 meters per second. Acceleration, we know, is equal to g, which is equal to 9.81 meters per second squared. And I'm going to go ahead and put that in as a negative. And what we're looking for is how long the ball takes to travel upward and come back down. Now notice that we're looking at VI. We're not talking about VF because there are going to be a couple different points in that, and in that ball's travel we could look at VI as it goes upward, VF as it comes to the top of flight and stops, and then we can look at VI as 0 again as it begins to fall, and VF as it hits the floor. We don't want to deal with any of that. That overcomplicates the situation. So what we have are VIA, delta y, and delta t. Do we have anything here that would get us those 4 things together? They go ahead and they solve for a final velocity. Oh wait, we can solve for a final velocity without encountering, without doing 2 bits of travel. Yeah, we could do that. Okay, so what if we use VF squared equals VI squared plus 2A delta t? Can we, in fact, there solve, how do they do it? They do that, and then they create a separate equation for delta t. Oh, that's messy, isn't it? That's ever so messy. I don't like that. Let's find a better way to do it. So, okay, here's one option. We can solve here for VF. Let's go down the road that they go down. VI squared plus 2A delta t. I'm going to shrink all these. And we have everything there that we need, but this ignores our displacement. And we don't want to ignore displacement. So we need something then that is going to tie together displacement with these things. Well, what about, 2A delta y. There we go. That has our displacement. But now that doesn't have, VF squared equals VI squared plus 2A delta x. Yes. A word of caution. Sorry, that was just my copying error. A word of caution. Every year I have one person who says, well, I'm just going to keep using delta x because I'm used to it. No, you're not. Here's why. Because in the next chapter we're going to be using displacements on both the x and the y axis, and you will have both a delta x and a delta y variable. So you have to shift gears and you have to think about your displacement on the axis on which it is occurring. Okay, so if we do this, we have an expression for VF which has VI, A, and delta y, which are all things we have. Now, could we do this? VF equals VI plus A delta t. Yes. And could we plug that whole mess in there? Yes. So what I'm going to do is I'm going to first solve for delta t in my second equation. I'm going to set this over here. I'm going to move all of this up. So VF minus VI equals A delta t. I can divide both sides by A, and that gets me a solution for delta t, and that's what I want. And I have VI, I have A. If I plug this expression in, that's going to connect that back to my delta y and my A. So that's going to put in all the variables I need. So square root of VI squared plus 2A delta y. That whole mess, and I'm putting it in parentheses only to make sure that if I'm a little sloppy, I know what's under the radical and what isn't. Minus VI divided by A equals delta t. Okay. Okay, so we plugged everything in, we substituted, did our substitution, and now we're going to plug in numbers and get a raw answer. Who got a negative answer for time? Anybody there yet? Keep plugging. Oh, you don't have a calculator? That's terrible. Okay, who has a raw number? So many of you have your thumbs on your noses or your fingers on your noses, or you're just giving me an otherwise sly smile that says, I have a raw number. Who has a negative number for time? Okay, here's why, and here's the problem, and it's a common problem, and you have to be really careful about it. So I wanted you to get that wrong number, because once you've fallen in the hole, you're less likely to fall in that same hole again. So what do we get under the radical? Let's see, we got 6 squared. Okay, so I have something that looks like this. Now here's the key piece. Plus or minus. What is this whole mess representing? Final velocity. What direction will the final velocity be? Okay, Michaela and Jillian, you've played volleyball apparently. When the ball is headed for the floor, its velocity is down. It's negative. So we know, I was just going for down, but yeah, you can say negative. It is negative. So we know that that final velocity has to be a negative number, which means that that plus or minus is a minus. So we get what, negative 8 point, so we get negative 8.674 blah 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 minus 6.0, and these are both meters per second, divided by negative 9.81 meters per meters per second squared. Okay, what does that get you for a rock? You get 1.4958 blah 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 blah. How many sig figs do we have? 2. So delta t equals 1.5 seconds. You shouldn't generally get negatives for time. Time is always positive. Time marches on regardless, and it is positive. There are a few cases, well, if we treat our signs carefully and you've gotten a negative number for time, something else is wrong, and it's a good red flag to go back and look at your problem. With that, all the 2F practice problems are assigned. Those are the book ones. So I'm going to have you get started on those, and then I will go get the worksheet for 2F. And once you've gotten through the book problems, which you should be able to do today, I'll hand you the worksheet. Okay? Go.